Hello and happy Tuesday, everybody. Today I'll be presenting the paper that's been the inspiration for most of my current research projects. The title of the paper is Intracellular Magnetophoresis of Amyloplasts and Induction of Root Curvature. It's by Oleg A. Kuznetsov and Carl H. Hasenstein. Carl Hasenstein is a plant physiology sort of person. He's studied heat stress in plants, nutrient concentration in certain seedlings, radiation, and of course gravitropism in this paper and in a few other papers, including working for NASA and sending seedlings into space. More on that later. Kuznetsov is a serial killer and a possible physics major. Oleg A. Kuznetsov is also the name of a Russian serial killer. He was in prison at the time of the experiment, so he's probably not the physicist involved, but I found the LinkedIn for the physicist who was involved and his ResearchGate. He doesn't have a photo on any of them, so I think he's just camera shy. The research that he does includes nanomaterials, flexible batteries, and many different applications of magnetism to biological systems. Their theoretical model is based on two main things. The first thing I want to point out is this one. So this is the force of gravity acting on amyloplasts. Generally, any buoyant body in a liquid will have a buoyancy, which depends on the difference in its density and the density of the liquid. So if this value, the density of the object, is lower than the density of the liquid, for example, if it were oil, the body would float on the surface of the liquid. So these are sort of opposing forces. Gravity is pulling down, but if this is less dense than the liquid, then this will push up. And so you might end up having a negative value for this, and that would indicate that the force is going upwards. So there's an analogous formula related to magnetic fields. So this chi B and chi L, this chi value is magnetic susceptibility. So you could think of it like sort of a magnetic density. How responsive is the material to external magnetic fields? And in this case, water is quite a bit less susceptible to magnetic fields than starch is, by about 50%. So then you're multiplying by the volume, which is just the volume of the material. How much of it do you have? And then here, this factor looks really hairy, and it is, but it's basically just an expression of the force that an external magnetic field has on a paramagnetic material, so a material like starch. We have just equated these two formulas to figure out how to make this value, this external magnetic field, strong enough to actually equal the force of gravity, to be on the same order of magnitude as gravity. And doing a little bit of algebra, the v's cancel out because they're the same thing. It's just the volume of the object. So you just get a ratio of the difference in densities to the difference in magnetic susceptibility times A. So that's acceleration, but really they just mean gravity. I don't know why they used a different letter, but I'll forgive them. We talked about buoyancy. They're very similar. Now, field strength needed. Basically, based on the earlier formula, they need 10 to the 9 to 10 to the 10 Oersted squared per centimeter. That's the unit. So these aren't SI units. This is a different system. This is the Gauss system of measurement. But it just means that you need a lot. So they went based on orders of magnitude rather than focusing on the exact number that they needed. The authors state an upper limit on what they can technically reach as 10 to the 4 Oersteds. They don't cite any supporting detail on this, but this is the difference in magnetic field strength in a gradient, which I'll talk more about later. So based on this formula, the overall magnetic force comes from 4 pi m times the external field plus 4 pi m again over d. So the reason we're squaring this is basically H external is really small. And as far as I can tell, what they did is they just said, well, we can get to 10 to the 4 Oersteds, right? We can do that. So we'll just put 10 to the 4 here, 10 to the 4 here. We'll square it. That gets us to about 10 to the 8 or 10 to the 9 if you multiply by that 4 pi. And then how do we get this value to be where it needs to be, which, as I said in the previous slide, we need to get 10 to the 9 to 10 to the 10. So we can get to the lower limit, but let's make sure we can really get higher. D is in centimeters. So if we divide it by 1 centimeter, it would just be 10 to the 8 or 10 to the 9. And if we divide it by 0.1 centimeters, it would be 10 to the 9 to 10 to the 10. If we go to 0.1 millimeters or 0.001 centimeters, we basically bring it from that 10 to the 8 lower bound all the way up to 10 to the 10. So they're saying, yeah, we can get from 10 to the 9 to 10 to the 10 as an order of magnitude if we have a field that's this strong. But it has to be acting over a very short distance, okay? So then the setup that they used was this wedge tip here. So this distance is about 0.1 millimeters. The whole width of the wedge is about 1 millimeter, but we're only concerned about this like arc length here. And it's a little unclear what exactly they mean there, but this is the formula they're using, and that's the D they use. They're also using that value for D in here, which is why they used 1.2, 3, and 5.5 millimeters. It was a little weaker doing this just because the gap is a little wider. The gradient of magnetic field strength is smaller, so they tilted it at a 45-degree angle, which meant the roots only had to be affected by 7/10 the force of gravity in order to be deflected. This is because the paramagnetic effect is acting as a vector with a partial downward component and a partial sideways component. So they just take the sine of this angle alpha, so sine of 45 is 0.7, multiply that by the force of gravity. That's the force that they need to experience. These are the two setups. They both create this really big gradient in magnetic fields over a very small distance. That was the point. And so they were looking at this in flax, Linum usitatissimum. Earlier experiments on Arabidopsis showed the same effect, but starchless mutants did not respond to HGMFs. Earlier results shown in the paper, they had this starchless mutant TC75. It's lacking PGM, which is phosphoglucomutase. It's needed to synthesize starch, so these plants don't have starch in their amyloplasts. Their amyloplasts are basically like empty shopping bags blowing around in the wind. None of the plants showed this curvature in response to magnetic fields. As you get increasingly widening gaps, because we're using this setup here with the gaps between two magnetic plates, the closer you get, the higher percentage of plants curve in response to that magnetic field. The next thing that they showed is that if you just have isolated amyloplasts sinking in a tube, they're displaced by the HGMF. So they just wanted to validate that this wedge could actually do this in a more ideal system. So they ran the experiment. They had a vertical plant, they had a horizontal plant, that's C, and then in B, they had a vertical plant with the wedge tip oriented this way. So starch grains will settle to the bottom when they're grown vertically. This lets the plant know where down is. When it's horizontal, they settle to the left. When you've got the high gradient magnetic field, they settle to the left because that wedge tip is pushing them, just like it's pushing these in this tube. But it's only really affecting the right side of the plant. The left side is still sedimenting normally. Okay, so then the next experiment they did is with plants placed vertically, rotated horizontally. I did a little diagram because I think it's helpful. B, the plants were placed vertically and the HGMF was applied from the right. Because the clinostat is rotating the plant around, it causes the amyloplasts to sort of settle towards the middle. So they're not sedimenting as they usually would. That means that they're more susceptible to this magnetic field. And you can see this borne out in the experiment. The HGMF is pushing all of these amyloplasts to the left side. Of course, this is more dramatic on the right side of the plant where the magnetic field is coming from. And you can see the same thing is happening with plants that are placed horizontally and rotated horizontally. But in the paper, they mention that this ended up having a greater susceptibility to that magnetic field, and the reason that they suggested is most likely because the cells are longer in this axis, in the vertical axis, than they are in the horizontal axis, so they're just more free to move. When it's rotating horizontally like this, they can move back and forth pretty easily. That meant they were more heavily affected by the magnetic field. The controls they did involved replacing the magnets in the previous experiments with aluminum wedges or aluminum plates, and those showed that the root tips were unaffected. They would just grow right next to the wedge tip. Then their other control was horizontal seedlings without a clinostat to compare amyloplast displacement and gravity versus magnetic fields. I did show that, so that's this image here, is the horizontal plant. So the other controls that they did were ruling out the effects of the high gradient magnetic fields on other physiological processes. They wanted to make sure that the magnetic fields weren't accelerating the growth of the plant in general, or affecting cytoplasmic streaming or something like that. They compared plants grown without any magnetic field to plants grown in a uniform magnetic field. So in the HGMF, they have the pin, and on either side of the pin, there are magnets, and that the uniform magnetic field between the two permanent magnets is made into a non-uniform high gradient magnetic field by the pin. You could think of it as like a magnetic lens, focusing that magnetic force into a very small area. So plants that were grown in a vertical orientation, so plants grown normally, in no magnetic field and in a uniform magnetic field were virtually identical in growth rate. In a horizontal orientation, they were slower to grow, but they were also virtually identical between the no magnetic field and the uniform magnetic field conditions. The reason for this is they're slowed down by having to curve. That's how they explained this in the paper, that when the root has to curve in order to move in a different direction, it slows down the plant's overall growth. The other thing they mentioned is that when a plant was horizontally or vertically clinostated, it actually decreased its rate of growth as well pretty significantly. So they say that these two effects interact, and that's why horizontally clinostated and vertically clinostated plants in the HGMF condition were the slowest to grow, because they have to cope with both having to curve in response to the HGMF and having this clinostating process where they're getting rotated. And so the future directions of the experiment, it was done a long time ago, so they have been able to follow up a few times. The first thing they were planning to do is to send this experiment onto the ISS in order to repeat it in microgravity. That was on shuttle mission STS-107, which was delivered by the Columbia shuttle. But that, as you might know, exploded on re-entry in 2003. The experiment was still delivered, however, and so they did follow up and they found what they expected to find, which was that in microgravity, roots will simply orient in response to magnetic fields. Now that we're in 2021, we can look at what we might be able to do differently with the technology we have now. They used samarium cobalt type magnets, and if you look at the hysteresis curve of samarium cobalt magnets versus neodymium magnets, you can see that they're higher up and more to the left. Both of those things are good. We like those things. So more kilo-Oersteds, more kilo-Gauss. There are different constants that people use to describe magnets, and it makes it pretty confusing because sometimes you'll get a rating for one magnet that's given in kilo-Oersteds, which references this value, or sometimes you'll get something that references this value that's given in kilo-Gauss, but you can't exactly convert it without knowing the hysteresis curve of that specific type of magnet. And, you know, there are also other physical constants that relate to the maximum value of the product between this and this. So it might be a value that's somewhere in here. And people won't say what exactly, like which constant they're referring to. So it just creates a lot of confusion. What I was able to glean is that in the paper, they mentioned that their field, which they used to magnetize their magnetic wedges, was 4,000 Oersteds, and N27 magnets, which are like $12, can generate something like 10,000 Oersteds. So we went from something like this to something like this in just a few decades. It's quite a significant leap. It's more than double the force, but it's still basically on the same order of magnitude as the original experiment. So it might be possible to sort of double the range at which this works. it would still only work on the range of like 0.2 millimeters at that point, which is still very small. You'd basically have to chase every root tip with your experimental setup in order to shape roots with that. So what does this have to do with crabs? I hear you all wondering. A paper published in 1893 is one of the first examples of magnetism being used to study gravisensation in biological systems. So crabs sense gravity with sand grains situated in their gravity sensing organs. So this person Cradle gave crabs an environment with magnetic sand grains in order to test whether that would alter their sense of gravity, and it did. So what if we could do the same thing in plants? What if we could take these amyloplasts, which are full of starch, which is paramagnetic, and replace it with some kind of material that is actually ferromagnetic, so something like hematite? It was sort of difficult to find tables of this magnetic susceptibility constant chi for different materials, but I found some mining engineering document that was looking at roasting hematite and its magnetic susceptibility as you roast it. So they're saying that after like 20 minutes, it's probably at its peak value. At this point, you've got sort of -2. This value is log x, so it's 10 to the -2, which means that you've got about 0.01 as the susceptibility constant. So I went ahead and put all of these values into Etsell, and if you use 0.01 and the density of hematite, which is about 5.17 grams per cubic centimeter, it spits out a value of this. There are two things that I want to point out. The first is the sign. This value is negative because the starch grains are repelled by that paramagnetic effect. Hematite would be attracted. That's why this value is positive. The other thing I want to point out is the order of magnitude. This is about 408,000. This is -6 billion. And that means that this is about 1,000 times weaker than this. So in the paper, they set the upper limit of magnetic susceptibility to 24,000, and that was the sort of maximum upper limit for the magnetic field gradient that you can practically create. So at that field strength, in order to get this number, you have to have about 0.01 centimeters or 0.1 millimeters of distance. You had to go with a very small number in this denominator to push that value a little bit further up to get to 6 to the 10. If you're using hematite, the same calculation yields a value of 1,409 centimeters. You should be able to move a hematite particle with this sort of gradient. That means that over the distance that you would need to build a large-scale structure, you could actually establish a magnetic field that was strong enough in its gradient to be sensed by hematite particles. So the units they give in the paper are in Gauss, but the value that they give for everything else is in Oersteds. So I don't entirely know how they got to this value, but I know that this order of magnitude lines up with what they were saying in the paper. So as far as I know, this is reasonable, but again, as with everything in this paper, it's more of an estimate. If you look at the difference in orders of magnitude here, this is about 1,000 times weaker. So the field needed to generate a force equivalent to gravity is about 1,000 times weaker for hematite. And so it makes sense that the scale it would work on would be about 1,000 times greater, which you definitely see here. Thank you for taking the time to listen to this talk. I hope this gives you a better background on the thinking going into my experimentation right now. At the moment, I've mostly been focusing on trying to recreate this, but the gaps I've been using are quite a bit larger. So I've had to kind of improvise and try to find a way to really focus that magnetic field and get stronger fields. I've been using these N27 rated neodymium magnets, so they should be stronger than what they had in the paper. I'm working more at a sort of centimeter distance. One thing that I'm planning on doing is introducing wedges like this inside the agar plates themselves, and having the permanent neodymium magnets on either side. So just like the wedge tip worked here, I'm going to have strong magnets on either side so that this can focus the magnetic field like a lens. Thank you all so much for watching. Special thanks goes to Connor and Sasha for their ongoing support through the Patreon and personally. In conclusion, putting plants in space is a good way to study gravitropism, but they might get revenge.